Welcome to this new tutorial series from Maxwell Zone, which will deal with the subsurface scattering and thin SSS materials in Maxwell Render. These types of materials have remained a mystery throughout Maxwell's career, so hopefully this tutorial series will let you begin to understand what you're doing when you're creating subsurface scattering materials and not just thinking that it's a voodoo magic and you're just sort of experimenting and hoping for the best. It's very important to understand the fundamentals of how subsurface scattering materials work in Maxwell. So in the real world, a translucent material is really a transparent material that has a lot of little particles inside of it that scatter the light. So it's not opaque, it's not transparent, it's translucent. And what happens in Maxwell is that it accurately mimics this real-world characteristic of a translucent material, so meaning that it is a true volumetric effect, because most other renderers sort of fake it by just rendering the effect at the surface. And this makes it so it's really not so easy to create materials that realistically sort of look more glass-like in the thin areas and really look translucent the thicker they are, which is really what happens in the real world because of those little particles inside. So, for example, if you imagine that this is a frozen dragon popsicle of orange juice, in reality it will look exactly like this. So the thicker parts will look translucent, and where they get really thin, it looks more glass-like, simply because we have less of those particles here that can scatter the light. And so this highly realistic effect is really automatic with Maxwell's true volumetric subsurface scattering material. And you can go from everything from very opaque looking translucent materials all the way to very a slight hint of translucency and everything in between. And you'll see that this is actually pretty easy to do, and hopefully it will become intuitive to you which parameters you have to change to achieve any kind of translucent effect. Now, because we're dealing with refraction, just like with glass meshes, your meshes where you want to apply translucent materials to, they need to be watertight, so no holes in the meshes, or you'll get sort of a darkening effect around those holes with translucent materials. So if you have a transparent material without translucency, it's a little bit more forgiving, but with translucency, you really need to make sure that your meshes don't have any holes in them. And the new nested priority feature in Maxwell is really great because it helps with a few problems where you have overlapping objects, and especially where both objects have translucent materials applied. So the nested priority feature, which is new in 3.2, really solved this very well. And it's important to keep in mind that it's not just applied to translucent materials, it's also very nice for overlapping transparent materials that don't even have translucency. So just to give you an example, here I have two spheres with a red and a white translucent material. So before the nested priority feature, Maxwell didn't really know which sphere was cutting into the other sphere. So you had these little artifacts here. You can see the darkening here on this side, and if I switch to the render with the nested feature priority, you can see that that darkening is gone. So in this case, I specified that the red sphere would actually cut out a piece of the white sphere. So we get an accurate effect. And this may not be so clear in this case because the artifact is pretty small. I mean, it's still ugly, but for example, this is a much more extreme example, and just so you realize that it's not just for translucent materials, this nested feature priority. So if you have water bubbles that penetrate a glass bottle and it's lit from behind, before the nested priority feature, it really didn't work so well, and now it works perfectly. You can see on the right. So The nested priority feature, you probably know this already, but just to recap quickly. So you specify here in the global properties of your material which priority the material should have, and 0 is it's not so intuitive, but it's the highest priority. So if it's 0, it means this material will cut into any other object where you have this material applied to. So in this case, this scene, the red translucent material is 0 and the white translucent material is 1. Okay, so of course it can go higher than that. So you can have let's say ice cubes which are in water, and the water is also surrounded by a glass. So then you can have more priorities to accommodate such scenes, and that's all you have to do really. So next in the fundamentals about these materials in Maxwell, so the true volumetric subsurface scattering and the thin SSS, they're two completely different approaches really. They share most of the parameters, but keep in mind that they're really computationally inside of Maxwell, there are two completely different approaches. So thin SSS really is meant only for single-sided surfaces such as leaves or curtains and paper, things like that. But you can also apply it to a volume, and we're going to check out some examples to see how well that works compared to, let's say, true subsurface scattering, or if it's better really in many cases just to have a single-sided object if you're going to use thin SSS anyway. And this is really the rule regarding the render time and the subsurface scattering in Maxwell really. The more scattering you have and the larger the attenuation distance, the longer your render time will be. So the more the light is allowed to go into the object and the more it scatters, you're going to have a much longer render time in those cases. And you're going to see the most extreme examples really are things like marble and porcelain, which look really fantastic with Maxwell's subsurface scattering, but keep in mind that those really are going to be the longest rendering materials you can have. Right, so now that we understand the fundamentals, it's time to dive into the parameters, and I'll explain to you the different relationships between the parameters in Maxwell, and which are really crucial to adjust, and which ones are really going to change a lot the look of your subsurface scattering materials. So before I start going to the specific subsurface scattering settings here, I think it's important to go over again the relationship between the transmittance and the attenuation distance for transparent materials, because hopefully this will also make it a little bit clearer the steps you should do when you start creating a subsurface scattering material, so that you know what you're doing. You're not just guessing what the parameters should be. So if I create a typical, let's say, red tinted transparent material, so I'm just going to use a roughness of 0, a common index of refraction, set this to red, and switch to hue saturation value. So I'm going to start with a pretty bright and saturated red, and make the attenuation distance something a little bit smaller so that we have a red tinted glass, and I apply it to these 3 cubes. Oh, maybe a little bit higher. Okay, so these cubes are, this one is 5 centimeters thick, 10 and 20. And of course, we get an accurate attenuation, and we basically get a red tinted glass. And the confusing part here can be, well, if the attenuation distance decides a certain distance that the light can travel inside of the material, but then again, the value of the transmittance can also decide that. So for example, if I set the value of this really, really dark, it's as if I'm also lowering the attenuation distance. You can see here all of them turn almost opaque. Okay, so this is the first confusing part, really. It doesn't have anything to do with subsurface scattering, really. It has to do with the relationship between the transmittance and the attenuation distance. So I came to realize that the value of the transmittance and the attenuation distance can be completely interchangeable as long as you're not dealing with color. So for example, if I just desaturate this completely and we're just dealing with grayscale, if I set the value here pretty high, so I get a more transparent material, but then again I set the attenuation very low to 1 centimeter, you can see that I get a less transparent material. But I can do the exact opposite, so I set the attenuation distance higher, but then I lower the value. Okay. In this case, I get the exact same effect because we're not dealing with color at all. But what I suggest to do is really not deal with trying to make a transparent material by playing with the value so much of the transparency, because most of the times, of course, you're going to deal with some colors here for the transparency or the transmittance. And once you have the saturation and the hue of the color, just by looking at the color chip really, then, leave that alone and then just start playing with the attenuation to have a more or less tinted glass, depending on how thick it is, of course. Because if you leave the attenuation distance, let's say too high, set this really high so we don't get any tinting, and you say, okay, well, this looks too bright now, or not enough tinted, and you try to start tinting your transparent material by lowering the value of the transmittance, what happens really is that you're just going to get a darker and darker material, less transparent, and you're not going to be able to bring out that tinted look of the glass. Okay, because we're dealing with color now also in the transmittance. So that's why I say the first rule really is, when you start working on a translucent material, determine first the overall look of the transparency, really the main color of the transparency, the saturation of it, and the hue that you want. And then with the attenuation distance, determine really how colorful it should be. And really based on the translucent material itself, of course, the more translucent it is, or the more opaque it looks, just by using common sense, of course, the light can go 5 meters into it, right? So that would not create a very realistic material. But just to have the color right, first of all, you should play with the transmittance, determine the color, and then go with the attenuation and change the attenuation until you have more or less the overall hue and saturation that you want for your material before starting on the subsurface scattering parameters. Okay, so now that I have the base color of my future translucent material, I can go ahead and start adding those virtual particles that will scatter the light inside my material. And I do this by changing the scattering here from anything else except black, and then changing here the so-called coefficient, or the scattering coefficient. And before going into what that does specifically in Maxwell, let's try to understand first of all what happens in the real world, again, in a translucent material compared to a common transparent material. So let's say you have this red tinted glass, and for transparency it's very simple. So you have light coming in here, and as it goes through the tinted glass, it takes on the color of the glass, and the light coming out of it is of course tinted in the color of the glass, and that's why you get colored caustics, and the glass looks red. Okay, so that's pretty simple to understand, and you may be wondering now, well, how do you tint the glass if you're not adding particles to it? How does it get tinted? And it does actually contain particles also. So tinted glass contains particles, but they're so small that they scatter the light in very, very small distances. And usually glass is colored by adding metal oxides to it. So different metal oxides produce different colors. And again, the concentration of the particles and also their size, especially their size, they're so small that they scatter the light in very, very short distances. So that's why you get a clear looking glass as opposed to a translucent looking material. Right? So the difference between transparent and translucency is that those particles inside the glass are now much, much bigger, and they catch more of the light rays and they can scatter the light much more, and thus producing a translucent effect. And really the complexity of understanding or creating, predictable subsurface scattering materials is that the color of those particles and their opacity, so you can have semi-transparent particles also, and that's going to give you a different translucent look. But most of all, what brings about the confusion is really the saturation and the hue of the particles themselves, because they're going to interact with the light that's also going to be tinted by the transmittance color. Okay, so in this diagram, try to keep it very simple. So again, you have light that's refracted in this transparent material, and as soon as it hits a particle, and let's say that these particles are tinted in blue, so then the light that goes through this particle gets tinted by the blue color in a combination of the red tint from the light in a combination with the blue, and thus it gives you a violet color. And then these violet light rays then go further into the object, and then they're further attenuated by the main transmittance color, so they turn a little bit red again, and then maybe they hit another particle, and then the same thing happens. And of course also the light itself is attenuated as it goes through the object and becomes weaker and weaker. And for example, the light rays that may be scattered up again towards the surface, maybe they hit a blue particle again, and thus they turn more violet again, and then finally they escape on the same side of the surface, and then here close to the surface we may see more violet light coming out. Okay, so this really makes the translucent material creation a little bit, or I should say quite confusing, just because these particles can have a different hue than the main hue of the transparent material itself. So then you really, if you take a look at the color wheel, just by looking at the color wheel, you can sort of get an understanding of what the translucent color is going to be. And so here, if the particles are blue and I have red light coming in, of course it's going to be a little bit violet. Okay, so let's try that as an experiment, just to mimic what I drew in the chart. So in the scattering here, I'm going to go through more details here, exactly what it means to have more value here in the scattering compared to the saturation. But for now, let's sort of just create a sort of pretty saturated blue particle, and then with the coefficient, I'm just going to set it to 1000. So the coefficient is really the amount of particles, but it's a little bit more complicated than that, but I'll get back to that. But let's just stick with trying to predict what the colors are going to look like in our subsurface scattering material. So if I switch this to the small subsurface scattering, and right now the effect is a little bit weak, so it's not so tinted, so the light goes too much into the object. So I'm going to lower the attenuation distance a little bit. Right, so we get that predictable effect thus far. So you can see that we get some violet light coming out here towards the surface, and as the light goes deeper and deeper into the object, the attenuation itself from the glass gets more and more important, so we get more and more tinted in red. If I try this in fire. By the way, fire is really not so good with subsurface scattering materials. You're gonna get faster renders actually just running a render in the viewport. You can see it's much faster and much cleaner than fire for subsurface scattering materials. Alright, so we get a sort of a violet material at the surface, and you can see that where I see the light going further and further into the object, it sort of gets a little bit more and more tinted towards the red. But most of the light that goes out to the surface immediately looks more violet. Okay, so it's a combination of those red and blue colors now. Now, before moving on and discussing in more detail what the effects of the scattering color and the saturation and the value and the combination of scattering coefficient do, here you have to understand really how crucial the attenuation parameter becomes for any translucent material. Because if you're just dealing with transparency, it's not going to make a huge difference if, let's say, you set this to 15 versus 10, for example. But because we're dealing with translucent materials, and because there is so much scattering going on with all these little particles, each time the light scatters, as it hits one of these little particles, it gets further attenuated. So this means that with translucent materials, you're going to have a much smaller, usually a much smaller attenuation distance. Otherwise, it would be impossible for those materials to look translucent. They would just continue to look transparent. So Maxwell doesn't really prevent you from creating very unrealistic materials. So for example, if I were to create a material that has a very high amount of scattering particles, but then you can set the attenuation distance to 5 meters. I mean, in reality, that wouldn't make sense because the light would get attenuated much more quickly since it hits all those little particles inside. So the attenuation distance would be maybe just a couple of centimeters. But if you do this, you're going to have, not only very unrealistic materials, but you're also going to have very unpredictable results, noisy results, and as you can see also, the colors get completely out of whack. I mean, it's totally unpredictable now what happens. Why am I getting, this hue now? Why am I getting sort of a yellow looking color that has nothing to do with the colors I chose here? So as a warning sign, really, when you start seeing little hints of the opposite color that you set in the scattering, and so in this case we're seeing sort of a yellow greenish tint here, and of course also these little dots here, you can see it really, this is never going to become clean. Actually, it's just going to get worse and worse in this cases. So these dots and the opposite hue becomes visible compared to what you set in the scattering. That's usually a warning sign that something is unrealistic in your material. Either too much saturation sometimes, and I'm gonna go in more detail regarding the saturation, but usually it means something is wrong with the attenuation distance compared to how much scattering you've set here. Right? So just again, thinking about this in common sense, it's impossible for a material to be so highly scattering, to have that many particles inside of it, and at the same time the light can go 5 meters inside of it. Right? So then we know right away that I should really lower the attenuation distance here, and things will go back to normal again. or become more predictable and less noisy and so on, right? So even in this case, maybe even 5 centimeters may be a little bit too much. So remember that the attenuation distance means what is the distance that the light travels through the object as it loses half its energy. So we're specifying that at 5 centimeters, it's going to lose half its energy. And with such a high scattering here, with so many particles inside of the material, it seems a little bit high. So again, I can lower it to maybe just 2. And now I'm getting again a pretty predictable result compared to the colors and the hues and the saturation here that I set. And another thing to keep in mind, especially when you're using high scattering values, is that you do have to wait a little bit to actually see the final hues, so to speak, because Maxwell, again, it's a volumetric effect. It's a true volumetric effect. So the more the light begins to scatter with these particles, the more it's going to change. And that's why you have to wait a little bit for these colors to sort of stabilize. So around sampling level 13, 14, even 15, that's when you can start to judge really what the final hues and translucent effect is going to be. So that also adds to the difficulty of working with subsurface scattering materials. But now you can see that it's pretty predictable compared to what we said here. I'm still getting a little bit of dots here. But that has more to do now with the saturation here that I set for the blue, which is a little bit high, and I'm gonna go into more detail about that. But in any case, the point I'm really trying to get across here is that be very, very careful with the attenuation distance when you're working with translucent materials, and it becomes even more crucial the higher you set the coefficient here, so the more particles you have in your material. Because if you start setting it too high with lots of particles, it's going to be a disaster in your renders. They're basically never going to clean. So maybe even less attenuation. And that just really makes sense because the light has to lose energy every time it hits one of those particles.